Hey guys, welcome back to the YouTube channel. Today we're going to be hopping on back to the technical train. As you recall in the last video, I kind of introduced myself, something that I should have done again in a very early video, but I just did it now. Better late than never, right? But today we're going to be going back on to technical topics with a CCNA 200-301 topic. In particular, this is going to be EtherChannel via LACP. So to start off our explanation of what EtherChannel is, I should probably explain what EtherChannel is. So EtherChannel is a technology that is built into a number of different vendors of switches and routers and networking devices. So for example, Microsoft calls it NIC teaming. There are a number of the networking vendors like Juniper who call it link aggregation groups, and Cisco happens to call it ether channeling. But they all accomplish the same purpose of bundling or combining multiple physical interfaces into a virtual interface. So let's have a look here, right? Because there are a number of reasons why you wouldn't want to do an ether channel. I'm only going to list a couple of them just to get you to understand, but there are a number of applications, a vast number of reasons why you would want to use an ether channel and have it dynamically negotiated using LACP. But to start off that, we should start off with some context. So here are two switches. We've got 4 links between them. It could be really any networking device, a router, switch to a server, whatever. In this case, I just have 2 switches, 4 links between them. Presumably, maybe this is an access switch and this is a distribution switch. It doesn't really matter the application of these switches. Point being, there's 2 switches and 4 links. Now, why would we want to have these 4 links? Why wouldn't we just have these just 1 link here? Well, there are a number of reasons. For one, like I alluded to earlier, assuming I can get my text mode back, we have reasons to have 4 links versus 1. We can have redundancy. So if any of these links goes down, we don't completely lose connectivity, which is something that would be pretty important if you're trying to connect an access layer to a distribution layer switch. The next reason that we might find it beneficial to have multiple links between network devices is load balancing. In a large, high-capacity enterprise network, it would not be unreasonable in some cases to expect that we have multiple gigabits of traffic flowing through our network device at any given time. If these were, say, 1 gigabit links, this link right here would be a bottleneck. If there were more than 1 gigabit of traffic coming in, this link right here would be a bottleneck. So we use multiple links to divide up the share of traffic, and we can handle that via protocols like Cisco Express Forwarding in the case of load balancing routing. But the point being is that we have these multiple links in place, and they're used to, again, divide up the share of traffic amongst the links so that we have an aggregate bandwidth. So let's say these are 1 gigabit links. Even though they're each just 1 gigabit, the aggregate bandwidth on the virtual interface that we create by ether channeling, or by creating a LAG, a link aggregation group, if we want to take this out of Cisco world, or by creating a virtual NIC team if you're on Windows Server, is 4 gigabits, right? So we take 4 1 gigabit links, we combine them together, and we get an aggregate bandwidth of 4 gigabits. No, we did not just enchant those cables with some magic. That's just the effect that we get of divvying up the traffic amongst those 4 links so that we can have 1 gigabit of traffic flowing on each of them. So we have redundancy and we have load balancing as our 2 biggest reasons why we want to ensure that we have multiple links between network devices. Again, whether they be switches, routers, switch to a server, it really doesn't matter. There are a ton of mission-critical network devices that require high availability and high capacity. That's why we use multiple links. Now, what are some problems with this approach of using multiple links and setting them up as separate physical interfaces? Well, firstly, there are a ton of features out there that look for just 1 interface. It doesn't take much effort to think of a Cisco IOS command where you have to specify an interface that only lets you specify 1 interface. It might not even be possible, or it may be messy to load balance between interfaces with those protocols and those features. An Ether channel solves that problem for us. An Ether channel will take these 4 links. Let me go back to drawing mode here with a marker maybe. These 4 links, and this is actually the symbol. It's an oval, but pretend this is an oval that's drawn well. The symbol for an Ether channel, if you're looking at a network diagram, is an oval that crosses these 4 interfaces. So this represents our one Ether channel. We call on Cisco it's called port channel interface. And so when we are specifying those features within the commands, when we're configuring those features and we have to specify an interface, we can just specify this port channel interface. And the switch itself will manage load balancing the traffic and failing over, because this port channel interface will always stay up as long as we've got one interface, or at least one interface that stays up, operationally up. So up. So if we've got at least one member interface that's still operationally up, this Ether channel interface, this port channel interface, will stay up. So if we have, let's say we have a failure, say Jimmy, the junior network engineer, decided that it would be a good idea to cut the fiber optic cable with a pair of scissors. Now that interface is out, we've still got these 3 that are going strong. Let's say that we've got, I don't know, some other idiot who decided that would be a good idea to cut 2 fiber optic cables with scissors. Now we've got this one interface still up, but our Ether channel interface, it's important to remember that it still stays up. As long as this cable isn't cut. Now, if this cable is cut, then the port channel will go down, right? Then the Ether channel interface will go down, our features will freak out, we'll get SNMP notifications, and yeah. But the point being is that that virtual port channel interface will always stay up as long as any one member interface stays up. That's a really useful feature to have, because if you have features that make direct references to interfaces, they might freak out when that interface goes down. But your port channel interface will never go down, even if one of its member interfaces goes down, as long as you've got one member interface that's still operational, that's still up. Now, why else would we use it? Why else would we use an Ether channel? Well, but besides that, there's one other reason. Well, there's a lot of other reasons, but there's one other reason I'm going to cover here. STP. Oh yeah, STP. So when we look at STP's purpose is to eliminate redundant paths in the network. STP will cut your redundant paths out of the network, and it's not like STP takes a pair of scissors like these idiot junior network engineers did and just cut the cables. That's not what STP does, obviously. STP will just put certain interfaces in blocking and thereby disable that link. So if we had these 4 links going to point A and point B, well, let's think about this. Now we've got, from point A to point B, there are 4 different ways that you could get there. So STP is going to say maybe this interface gets blocked, this interface gets blocked, and this interface gets blocked. There's a whole designated port election process that determines how that happens. But the point is, because this interface is blocked, this is no good. This interface is blocked, so this link is no good. And this link's no good because this interface is blocked. The only link that we have operational is this. Doesn't that kind of kill this objective? Doesn't that kind of kill our load balancing potential? If we only have one of these interfaces, one of these links that are operational at any given time, doesn't that really kill our potential of being able to load balance across this? Now, true, SCP will react with a topology change when this link dies, and it will bring up one other link, but it will always ensure that from point A, draw a circle, to point B, draw a circle, that there is only one valid path, that every other path has some blocked interface that serves as an obstacle to it working. Well, an Ether channel is special because it's a port channel, right? The port channel represents all of the other physical interfaces. What that means for us in terms of STP is that STP will not even consider these 4 physical interfaces as 4 separate interfaces. STP will consider the topology as this. And this link is the port channel. So with this, in STP, if you actually run we'll do this in a demonstration, if you run a show spanning tree, and you look at the interface listing, it will not even show you that the physical interfaces are detected by STP. They still exist on the network device. They are still up. They will still react and turn down if you say unplug the cable or issue the shutdown command at interface level, but STP doesn't see them. STP just sees that port channel, and it sees it as one link between A and B, even though we as network engineers know that there are actually 4 links, in this case, between A and B. So that's some of the reasons that we would want to use an EtherChannel. We either want features that only take one interface as a configuration input to still work with our failover between multiple links, or we want STP to detect the port channel as one link so that it doesn't shut down the other links and take rid of our load balancing abilities. Granted, if you didn't use an EtherChannel, the redundancy aspect would be kept, because once that link failed, that STP selected as the only link that was allowed to be used, it would select the other link, and the other link, and the other link. And the list goes on until we run out of links to connect A and B. So even though our redundancy is still there, our load balancing is not, and that's why we use EtherChannels to make STP detect the link as one link instead of 4 links, where it has to choose multiple interfaces to block off. There are a ton of other reasons you might want to use an EtherChannel, but those are some of the ones I'm going to cover. So that's a quick theoretical explanation of what EtherChanneling in general is. Now let's get into what LACP is, because as you saw in the screenshot that I edited into the video earlier, the Cisco CCNA 20301 exam objectives specifically mention LACP. So the old CCNA RNS, and you may be familiar with this if you were studying for the old CCNA RNS and maybe ran out of time because of Certpocalypse, but the old CCNA RNS covered 2 ways of dynamically negotiating an EtherChannel, because an EtherChannel is a special type of ordeal. You on both switches or both devices that are involved in the EtherChannel, they have to be aware of the EtherChannel. So I can't just say on switch A, you know what, hey, let's make an EtherChannel, and switch B still be completely unaware of that. That won't work. The EtherChannel has to be negotiated between both sides, and there's 3 primary ways to negotiate an EtherChannel. There is LACP, PAgP, which stands for the Port Aggregation Protocol. There's also LACP, which is the Link Aggregation Control Protocol. And then there's manually defined. I'll show off all 3 ways, even though you really only need LACP for the CCNA. It is valuable to know the rest of them. But LACP is just a protocol it's an open standards protocol defined by the IEEE that we can use to negotiate port aggregation. So LACP is valuable because it allows us to negotiate EtherChannels between multiple vendors. This could be a Cisco switch, and this could be a Juniper switch, or this could be a Cisco switch, and this could actually not be a switch, but like a Windows server. Fun fact, Windows Server NIC teaming supports LACP if your switch supports it. But if this were like a Windows server, for example, you could use LACP to negotiate the EtherChannel between them. In Windows Server, again, it would be called NIC teaming, but you get the point. We can negotiate the link aggregation. PAgP is a Cisco proprietary way of doing that, and then manually defined is just you going on that switch and saying, hey, I'm going to manually aggregate these 2, but the catch is that you have to do it on both sides. And we'll go ahead and overview the configuration commands in a bit. Alright, so I stopped the video to go ahead and start up my devices and assign host names and everything, kind of experiment to make sure the images are working properly anyway. So we're going to be going ahead and creating a layer 2 EtherChannel. So there's actually 2 types of EtherChannels, layer 2 EtherChannels and layer 3 EtherChannels. You might be asking, what's the difference? And the difference is actually very close to the difference between a switch port and a port when I say no switch port. So when I say switch port, the default configuration is switch port. It's a layer 2 switched port. What does that mean? Well, it can't be routed. So I can't assign an IP address. I should not be able to assign an IP. Oh, I'm sorry. See, yeah, it was a routed port. Anyway, this IP address right here, this IP address command doesn't work. Unrecognized command, because this is a switch port. But if I say no switch port, I turn it into a layer 3 routed port. So now I can add an IP address to it. Now, this is a similar thing to what we were talking about when we talk about layer 2 EtherChannels and layer 3 EtherChannels. A layer 2 EtherChannel, when you create the port channel interface, that virtual interface that represents all the member physical interfaces that you'll see in a moment when we actually configure the EtherChannel, that port channel interface in an EtherChannel configuration, a layer 2 EtherChannel, is a switch port. In a layer 3 EtherChannel, it's a routed port. And it's an important distinction to make between layer 2 and layer 3 EtherChannels, not only because of the differences between the port type of the port channel interface, but because there are actually different configuration steps. Well, not necessarily different, but a different order of configuration steps when we're talking about layer 3 EtherChannels. But for now, we're just configuring the layer 2 EtherChannel that we're going to start off with. Now, if we go back to show CDP neighbor here, you can see we've got Gigabit Ethernet 00, Gigabit Ethernet 01, Gigabit Ethernet 02, all going to switch 2. Now, if I do a show spanning tree, it's actually, oh, this may actually, here we go. So, the reason for this was that this was the root bridge, but let's go over here. So you see that these 3 interfaces, only one of them actually works. This Gigabit Ethernet 00 interface is a root port and it's forwarding. The rest of these are blocking. So the reality of it is that we have 3 ports over here that display designated, forwarding, but only one of them actually work because this interface is blocking. It will not allow any data on it, only control packets. So we want to change that. We want to get STP to not block those interfaces and to instead only recognize one virtual interface, and that's that port channel. Well, what do we do? Well, you could certainly, there's a command that you have to apply to every single interface. There is certainly a way that you could do that by saying int g00 and then the command, and then int g01 and the command. I'm too lazy to do that, so I'm just going to do an interface range, and I recommend you do the same if you're labbing this. That way I don't have to type this command in once, because it is a fairly decently long command. Now, before I actually show you the EtherChannel configuration command, there is one command I want to show you. It's a channel protocol command. So when we go to configure our channel group command, there are a lot of keywords we can use. And some of those keywords correspond to PAgP, some of those keywords correspond to LACP. If you want to manually set the protocol so that you don't accidentally use the protocol or the keyword of another protocol, you can set it from here. Let me show you what happens if I set it to PAgP and then try to use an LACP keyword. So the actual command to configure an EtherChannel is channel group. We'll have to provide a group number. This is the EtherChannel number 1, let's say, mode. And here we have a bunch of keywords. So active, as you can see, active and passive are LACP, LACP. Auto and desirable, these are PAgP keywords, and then on is our manually defined EtherChannel. So we go back here to our 3 primary ways of defining negotiating EtherChannel. This is what we see again: LACP, PAgP, and manually defined EtherChannel. We'll start off on LACP just to show you. Keep in mind, I've configured this command, this channel protocol PAgP command. Before I do this command, if I do a show run interface G00, you'll see channel protocol PAgP, and And if I do channel group 1 mode active, it errors out. Command rejected. Channel protocol mismatch. For interface give Ethernet 0, 0 in group 1, the interface cannot be added to the channel group. And the range command, because it is an interface range, it says the range command is terminated because it failed on any one of the member interfaces. But this is the key here. Channel protocol mismatch. That is our key. So I tried to use a LACP keyword when I manually specified PAgP as the EtherChannel protocol that was to be used on interface, and the switch went, nope, you are not allowed to do that. So let's change our channel protocol to LACP. And let's say channel G, that's short for channel group, 1 mode active. So now we have an LACP neighbor relationship, or not neighbor relationship, EtherChannel. And you'll see, if I run show IP interface brief, we have this port channel right here. Now this port channel is down because if I do a show EtherChannel summary, this is one of our verification commands, show EtherChannel summary. There's actually a ton of EtherChannel commands you can use right here. We're looking at summary. You can see SD. If we look at our key, D means down and S means layer 2. We'll see R when we do a layer 3 EtherChannel, but for now, since we're doing layer 2, this is an S. It should say SU because U, if I can find it, is in use, meaning it's up. The EtherChannel is up. So what's our issue? Well, keep in mind that LACP and PAgP are dynamic EtherChannel negotiation protocols. So if you've covered routing in any extent at all, you'll know that OSPF has their OSPF adjacency. Well, for an OSPF adjacency to be negotiated, you have to have both routers in the program, right, on the same page. Router 1 has to want to negotiate an OSPF adjacency, and router 2 also has to want to negotiate an OSPF adjacency. If either of them don't have OSPF configured correctly to where they're actively trying to establish an adjacency, it won't work. In the same way that this port channel is down because it's only been configured on switch 1, I need to do the same thing on switch 2 to configure it. So we will. It is worth noting that the channel protocol command is not required. In fact, I'm going to do it without the channel protocol command, and you'll see that that works perfectly. Although, here's one more thing I want to display. Desirable is PAgP. I configured LACP right here. See, protocol LACP. What if I try desirable? Seems not to error out. Uh-oh, we have up, down. That's not good. Uh-oh, our port channel is down. Well, it did come back up, but... Uh-oh, this is not being negotiated properly. And I standalone? Why is it not working? Well, we can compare. LACP. PAgP. I need to get these to match. So, that right there is a demonstration that, yes, you do need the negotiation protocols to match. Oops, I should probably remove the no keyword. And the second I do that, after it negotiates, after the LACP DUs go through. So if you remember from your STP studies, STP has BPDUs, LACP has LACP DUs, LACP data units. Sorry there, I had to cut off my video because my switches were acting funny. I reloaded them and they seem to be working now. So the EtherChannel, this is how it's supposed to look. This is how a layer 2 EtherChannel is supposed to look. So we have port channel 1, SU, so S means layer 2 capital S. Don't mistake it with lowercase s, which means suspended. But here's our capital S layer 2, here's our capital U in use. And if we go look for the port channel, you can see port channel 1 unassigned, up, up. So that's the important thing, right? Now we have a function EtherChannel. If I go on switch 2 and I run the exact same command, you can see up, up, and if I do a show EtherChannel summary, there we go. Show EtherChannel load balancing, right? How are we, because remember, as I mentioned, the reason that we have multiple links, one of the reasons anyway, is for load balancing. So how does the EtherChannel help with that? Well, the switch operating system will actually perform load balancing for us. So in this case, we can see it's based off of the destination IP address for IPv4 and the destination MAC address of its layer 2 traffic. There's a ton of other verification commands here as well. The one that I can most confidently say you'll probably be using most often is show EtherChannel summary. And you'd be using that just to make sure that the EtherChannel is up and functioning before going on to any troubleshooting steps. But as you can see, our ports are P, which means that they're bundled in the EtherChannel. And if you go up into detail, see state BNDL bundled. And you would see the same thing if you did on switch too. So that's when it's negotiated via LACP. LACP has some interesting things that when it comes down to fine-tuning how LACP works. I'm not going to get into that in this video, maybe in a future video, because this is just supposed to be a basic configuration, but that's what that is. So with that out of the way, let's go on to what keywords we can use to create an LACP EtherChannel. So before we go on to PAgP and manually defining the EtherChannel, we need to make sure that we understand what these keywords mean. So in the case of LACP specifically, we have active and passive. So the difference should be kind of obvious. So in an active state, the switch is trying to, or switch or network device is trying to actively negotiate the EtherChannel, actively sending out those LACPDUs and trying to hit up the other switch and say, hey, yo, you want to negotiate this EtherChannel? Whereas passive only activates if there is an LACPDU received. In other words, a switch that has, or again, any other network device that has LACP set to passive will not go out and actively try to find LACP neighbors, but rather will only activate an EtherChannel if another neighbor tries to solicit an EtherChannel relationship. And I created a little helpful matrix here. I know, sounds Star Wars-y, but oops, that's not how you zoom in Microsoft Excel. But just zoom in here. Yes means that there is an EtherChannel formed, and no means that there isn't. So you can see 75% here. We do have an EtherChannel forming. So the important thing is that you have to have at least one active somewhere. So actually here there are three combinations. You can have active-active, active-passive, or passive-passive. Active-active, yes, because there are two sides of the relationship that have active. Active-passive, yes, because this one side right here is passive, but that's okay because you have someone who is actively going out and soliciting an EtherChannel to be built. So that passive network device receives the LACPDU and says, okay, let's go ahead and start up an LACP relationship. Let's go ahead and build this EtherChannel. Passive, no. And the reason for this is actually the most logical thing ever. So if you remember, I'm going to keep saying this. Passive network device in LACP means that it will only create and build an EtherChannel if it is solicited by another LACP device. When you see here, it's not neither of them are going to go out and actively solicit a EtherChannel to be built, and both of them are listening for the other. It's kind of like when you're on the bus and you have a stop coming up, but you think someone else has got to pull your stop, so you don't, and no one else does it. Yeah, I know. That's what this is. This passive neighbor is waiting for another network device to solicit a relationship that's never gonna be solicited, and same thing, vice versa. That's why this never gets built. We have the active-active, yes, active-passive, yes, because in each instance of this, we have at least one network device that is going out and, again, actively soliciting an EtherChannel. So, and the same thing applies, because a lot of these verbs, when we talk about PAgP in a second, Desirable and auto. Auto is synonymous to passive. Desirable is synonymous to active. They have virtually the same meaning, except that a set of them are used to activate LACP and another set is used to activate PAgP. So here is how we define a PAgP based EtherChannel. It's the exact same way as a LACP EtherChannel. Let's actually go ahead and say no channel group 1 mode active. Forgot that. And I'm going to go ahead and manually set a channel protocol to be PAgP. You can see the side errors out because it said EtherChannel don't bundle. LACP currently not enabled on the remote port, so it's suspended the port channel. You can see port channel changed to down. Let's go ahead and go over here, and we'll go ahead and say no channel group 1 mode active, and then we'll say channel protocol LACP, or PAgP, I'm sorry. And now we'll say channel group 1 mode desirable. Because remember, desirable is our way in PAgP of saying active. So this is the same as active, right? So you see, our port channel came up. If we do a show EtherChannel summary, it's the same verification commands because it's also an EtherChannel. You can see SU, which is good. It means that it's layer 2 and up. We can see P, so that means that the interfaces are bundled, and PAgP. And if I do a show EtherChannel 1 detail, you can see over down here, we have, I'm looking for, it's also nice that you can look at a key here. But point being, it is up. Now if I go to the other switch and do the same thing, same thing here. We have a working EtherChannel. Can't think of regular expressions. Port channel 1 up. So that is PAgP. If I want to say, I'm going to use this opportunity actually to demonstrate passive. Let's wait for this to come up. And you see, same effect, it's up. But if I go on switch 2 and say, well, I wonder if I can just do this. Yep. You can see our port channel is down and nothing is being negotiated. SD, which is not good. W is waiting to be aggregated. You see here? And I is standalone, which is not good. That means that they're not bundled. SD down. That's because we have, and you can see the port channel went down on the side. That's because we have both sides that are passive, and they're waiting for the other to solicit them into an EtherChannel, which is not going to happen. So we have to get one of these sides on board with the plan, which I'm not going to do right now because I'm going to just go straight into doing a manually configured EtherChannel. So in this instance, nothing's really being negotiated. It's just straight up doing an EtherChannel. If I do channel group 1 mode on, oops, see, command rejected. No channel group 1 mode auto. Channel protocol mismatch. That's why we have that channel protocol there, to protect us against making stupid mistakes like that. But in this case, we actually want to do that. So when it's on, you can see that it just straight up goes into an up state, SU, and it's bundled, right? This doesn't necessarily mean that it's working, and that's one of the things that you can run into when you do channel group mode on, is that because there's no sort of negotiations, there's nothing that protects this side from being misconfigured. There's nothing that protects against misconfigurations. There's nothing that detects it. There's no negotiation process of any sort. It's just this is now an Ether channel. It's forced. Now, that's okay if I go on this side and also say that I want this to be no channel group 1 mode auto, no channel protocol, channel G, and this is shorthand by the way, channel G and channel P for group and protocol respectively, 1 mode on. See, my port channel will come up nearly instantly, and this is fine. Honestly, if I set up a VLAN interface right here and try to ping between them, keeping in mind, of course, I have to no-shut the VLAN interface. I ping right? This ping works across this EtherChannel interface. Now, if I, let's say, set no channel group 1 mode on, channel G 1 mode desirable. So in this case, I'm using PAgP. My port channel is down, and if I try to ping across, you can see that it no longer works. So there's nothing protecting us. There's nothing here that would indicate on the switch at least that it's not working because it's forced to be on. That's why in general you want to be using some sort of dynamic Ether channel negotiation protocol, and you should be using LACP unless there's a good reason for you not to be, primarily because it's open vendor and it's more advanced anyway because you have more fine-tuning capabilities. PAgP is sort of like a plug-and-pray approach to Ether channeling. Now, we're going to go into configuring a layer 3 Ether channel. So configuring a layer 3 Ether channel has a lot of similarities to configuring a layer 2 Ether channel and quite a number of differences. So the differences start with the actual member interfaces themselves. So a layer 2 Ether channel was a layer 2 Ether channel as I described earlier because the port channel interface that comes after the creation of the Ether channel is a layer 2 switched port. But that's not the only reason. Part of the reason as well is because the member interfaces are also switched ports. If you'll recall, I didn't do any kind of no switch port. In fact, this is a switch port, right? Even I just entered a switch port command, but these were switch ports to begin with. And so when I create the channel group, when I went into here and said channel group 1 mode, whatever, LACP, PAgP are manually defined, you could see that they formed a layer 2 Ether channel. I couldn't assign an IP address. I can't assign an IP address to any of these interfaces, right? It's just an recognized command. Now, a layer 3 Ether channel not only creates a layer 3 port channel, but also requires that its member interfaces are layer 3 routed ports. So what does that mean? That means that before I go and define a channel group, I have to say no switch port. These ports all have to be converted to routed ports such that I can now apply an IP address to them. Now, there's one other catch. The rest of the configuration steps are darn near similar, but this is the only step that's kind of weird. So as you'll recall, when I configured a layer 2 Ether channel, and I set channel group 1 mode on, let's see if I can find the message somewhere up here. If not, it's okay, but it doesn't seem like I can find it. But there was a message, if you can go back in the video you want to see it, there was a message where it said creating a layer 3 port channel, or not port channel, creating a port channel interface. So the channel group command in a layer 2 Ether channel created the port channel interface for us. So when I went into show IP interface brief, there was one additional virtual interface from before I create the Ether channel and define the channel group to afterwards. But with a layer 3 Ether channel, I have to manually define the port channel interface before I define the channel group. You can also do this with a layer 2 Ether channel, but it's not strictly necessary. With a layer 3 EtherChannel, it is necessary to create the port channel before you define a channel group. So let's do that. And it is important to note, when I say this is something similar to creating a loopback or creating a tunnel interface, right? It's similar to me defining a lot of different virtual interfaces. But I'm going to say port channel, and it's going to make me define a number, 1 to 48 in this case. It is important to note that this number has to match your channel group command. So you'll recall that in the channel group, I specified a group number. That has to match up with the port channel interface number. If you recall, when I created the channel group and gave it a number of 1, it created port channel 1. If I gave it a number of 2, port channel 2, and so on and so forth. So when I define this interface number, it's the reverse. Now that I'm defining the interface number first, I have to create the interface with the number that I want to specify in the group, not the other way around. So let's say, screw it, 46. That's all we, actually, that's not all we have to do. I have to say no switch port, because now I have to, it's going to error out if you don't do, if you try to add a layer 3 member interface to a layer 2 port channel, and vice versa. If I try to add a layer 3 interface to a layer 2 port channel, it will also similarly error out. The port types have to match. So now I do a show IP interface brief in port channel. You can see, actually this port channel isn't gone. I should probably do that. You can see port channel 46 unassigned down. So let's fix that down. We're going to say int range C00 to 2. Again, just make sure there are no switch ported. And then channel group 46 mode active. You'll see that is a very, very similar command. Actually, the same command that we would have used if this was a layer 2 EtherChannel. It just differs in the order of events that we use. And you can see layer LACP is not enabled in the remote port. Let's go over here and enable it, shall we? So we're going to say no switch port. We're going to say interface, port channel, and the port channel numbers, the group numbers are locally significant. Just to prove that fact, I can say 34 over here. No switch port, int range C00 to 2, channel group 34. They do have to match up between the commands channel group and the interface that we defined, but channel group 34 mode active. And pretty soon we should, assuming these images don't break on me again, have an EtherChannel that comes up, and we can see a link interface port channel 34 change state to up, and we have a line protocol changed up. If I do this, we can see I should probably again delete this port channel interface. Port channel 34 unassigned up, and over here we can see that this port channel also came up. If I run this show IP interface brief command up, if I do a show EtherChannel summary, last time it said SU, but now because this is a layer 2 EtherChannel, it says RU. RU meaning layer 3. And all of the previous concepts that we talked about active versus passive, desirable versus auto, manually defining EtherChannel, PAgP, all that stuff transfers over. The only difference is that was being applied to a layer 2 switched port channel interface. Now we have a layer 3 routed port channel interface, which means that I can go to this port channel and manually directly give an IP address that will directly refer to that interface. So if I say 192.168.1.12552552550, I should probably remove the IP address from VLAN 1 before I do this. If I ping from switch 2 to switch 1, oops, you can see that it works. It works over this layer 3 port channel. And just to prove EtherChannel's usefulness, let's say that for some reason there's a cable cut. Some idiot cut the fiber. In this case, I'm just gonna do a do a shutdown on any one of these interfaces. You can see that list changes down, but my port channel is still up, because I've still got 2 other member interfaces that work. So if there's a feature that refers specifically to the port channel, well, it's not going to react, because we've got 2 memory interfaces that are up, compared to if we had maybe 3 configuration statements for the same feature, each with a different interface specified for G00, G01, and G02, maybe this interface going down would have caused some domino effect that we didn't want. Well, by having this port channel and referring specifically to the port channel, now we're relying on the switch itself and its operating system to control the state of the port channel based on whether any of its member interfaces are still operationally above, which in this case we've got 2. Now, if I go here and shut down both of these interfaces, now the port channel goes down, because now it has no member interfaces left. But assuming that it has at least one member interface that I can use, even if its load balancing capabilities are cut, it will still stay up, which is, again, good news for any features that are specifically relying on that port channel to have a specific reference to it and are tracking its state. Example being if you were to use like a track object per se to track the interface line protocol or track the line protocol state of this port channel, right? If I had separate track interfaces for each physical interface, one of them would trigger as soon as any one of the interfaces went down, but if I refer to the port channel, it will only go down as soon as all the connectivity between these 2 devices, all the member interfaces in this port channel are gone. So, that concludes my explanation of layer 2 and layer 3 EtherChannels. It concludes my configuration demonstration. It concludes my explanation of what an EtherChannel is in general, why you would want to use it, what its advantages are compared to just having multiple links between switches that are treated as separate physical interfaces by the switch's operating system. And we went over in the beginning why we would want redundant links across multiple devices anyway. So with that being said, I hope you guys have an awesome day. Hope you guys keep doing more Cisco. I hope you guys stay safe in this coronavirus pandemic. Keep listening to the scientists and the experts who are giving us more and more advice every single day. And yeah, yoy! Make sure to drop a sub, drop a like, drop a comment, and hit that notification bell to be notified about any more videos. And if you're a CCNP candidate, don't despair. I've got fun MST and RPVST integration lab coming next in a separate video. So I'll see you there. Have fun, y'all.